Welcome back. This is just a summary of what all we saw in week 3 and what its significance is. We started, if you remember, with trying to generalize the linear model that we had last week. We saw that many models can be written in a linear form. The general trick is that if you have any model and it can be written in the form y hat equal to some w0 plus some w1 times, I have called it x1, w2 x2 up till wn xn, and in fact this could be some other function of x1 also, and this could be some function of x2 also. Any of these cases is linear provided it is linear in the parameters. Okay, so linear in the parameters means it should be linear in w0, w1, w2 and wn. So that is where we started. That is what we call a generalized linear model. Now what was important was, even if we have a generalized linear model, if you want to solve, keep on solving del j del w 0 equal to 0 etc., and all these equations we saw last week, that is cumbersome. Even for a quadratic model with just 3 parameters it got painful, but you can write a general matrix form provided you do a few tricks which we did this week. So we had this X, which was a matrix, which, as I have written here, every row is basically sort of a row in an Excel sheet. This contains all the input vectors appended with a 1 in the beginning, and you would have something like x1, x2, x3, where x1, x2, x3 are features. These are called features, or another way to think of it is these are components of the input. I gave you the example. These could simply be Cartesian components. For example, x is a location vector, and if you are in 3D, then x1, x2, x3 would literally be the x, y, z coordinates. Or x could be something more complicated like temperature and pressure, or temperature and heat flux, and you are measuring something else. Now if you have something of that sort, in general, since we are doing the general case here, in general it is just going to have multiple features, and we store each data point. Okay, so again think of these as each of one corresponds to a single data point. So the first data point will have multiple input features, and the ith data point will have n features with one appended here in order to make the model work. In that case, if we write W itself as a matrix W0, W1 up till Wn as an n cross 1 matrix, you can then write this equation, which is the general linear model. And if you write it as this general linear model, in fact, if you would have seen an advantage of doing so while we were writing our code, you can write the del j del w equations, the optimal equations, as the normal equations, and it reduces to a system of equations which is x transpose x. This is the matrix you are solving, or this is the matrix which sits on the left hand side, multiplied by w is the right hand side, which is x transpose y. We will see an extension of this next week when we go to nonlinear regression. So we will see that this equation is not just what it appears, it has certain other subtleties which I briefly alluded to this week, but we will see a more general case next week. In any case, we saw that using this kind of approach actually easily lets us go from linear to quadratic to polynomial to many types of models, and this can be easily programmed in a compact fashion. So that is the advantage of having a general linear model. Now apart from a model which looks linear to start with, you can have models that do not look linear in the parameters. I am not talking about linear in the features, but linear in parameters. So you could have terms like e power w. Okay, e power the parameter you are solving for. If the parameter you are solving for is a, it could have terms like e power a, as we will see shortly, or something power a parameter, etc., etc. So all these things are not linear in the parameters, but we can make them linear. And the important thing is the final expression. Again, I am just repeating the statement from the previous slide. The final expression should be linear in the parameters. It need not even be the initial expression. You just have to transform it into a form. So here are some examples we looked at this week. Many of the examples can simply be linearized by taking a log. For example, if you have, let me take this example, this can be converted into a linear form by taking log. So, you have ln a plus bx, as you can see, this you can call y hat, this you can call w0, and I literally did the same example earlier, but this is just to jog your memory that you can actually turn something that looks non-linear into linear. As I also told you within this week, this form can occur within fins. We are taking simple cases. So, for example, a fin with a infinitely long condition, basically meaning that it is much longer in comparison to its thickness, in comparison to its width. So, in the this case you can actually use this approximation, and we will in fact, at least we will see some exercise problems etc. as we go on in the course in such cases. You could also have things that do not look linear here, and if you carefully handle it, as I showed you this week, you can turn it into something linear. However, there are cases that are not linearizable. Okay, this does not mean that every single case is linearizable. There are some cases we will come to which are non-linearizable, and this is where next week we will switch to nonlinear regression to handle such cases. Okay, so, here is an unsteady, again an unsteady convection case in some sense, which is non-linear, which is you have to handle with nonlinear regression. The next idea we looked at was a parity plot. This, as I told you in the beginning of this week, is basically a visualization technique for a general model. What do I mean by that? The entire effort this week was to extend it to cases that look more than just w0 plus w1 x. So, if you have x1, x2, x3, xn, you cannot do this kind of visualization which is just x versus y or x versus your predicted variable, because x is now multiple variables. Now, how do you handle such a case? Now, instead of plotting your features versus the output, you just plot your y versus your y hat, which is always just single, or at least you have a maximum of 3 or 4 predicted variables. So, you just have 3, 4 2D plots. The idea here is to plot this ideal line, and this line shows how well our model performs. Okay. So, you see in fact in some sense it is switched. In this case the dots here represent reality and the lines here represent the model, and it is kind of flipped in how a parity plot works. So, in this case the ideal is a 45-degree line, and the model, depending on how far it goes from here, you can then start identifying things that are really far off and start examining whether your sensors are working properly or whether their accuracies are desirable or not. And in case it looks like you have given equal weightage to lines which you shouldn't have given equal weightage to, we will come to weighted least squares. So, that is one way to approach weighted least squares, is to notice that some points seem to be too far off from our model, and if we are confident about our theory, we can then start examining, is the accuracy of the sensor good or not. Okay. So, if the accuracy is not good and each point has a different accuracy, then we can start thinking whether we should reweight each accuracy. Okay. So, as I have mentioned here, it is useful for high dimensional or high feature cases. You plot y versus y hat and you can visually see the difference, and allows you to see outliers, and perhaps you can move to weighted least squares if required, I mean if we find something off. So, the final topic we did this week was weighted least squares. So, consistently we have been minimizing y minus y hat square, but however, just like I mentioned in the previous slide, let us say that if all data points are not equally reliable, so these have different accuracies, or you plotted a normal least square line and then you observed, as I showed you last time, that there is some outlier, you start examining and it turns out, let us say that the thermocouple is old, its error has increased, its standard deviation has increased, something of that sort. In that case you can put weighted least squares. Okay. Weighted least squares have this extra factor here, and this corresponds to lambda I equal to 1 by sigma I square, and sigma here is the standard deviation of the sensor. So, suppose you make, let us say, a known temperature, you measure it 100 times and you see a certain standard deviation within the sensor, you measure it and say, okay, so you have to calibrate your sensors, find out your thermocouples, let us say, and then you say, okay, the variance is so much. And then if not all of your thermocouples are equally inaccurate or equally accurate, you will have to weight them differently. The solution in the normal equation sense, which I just wrote, I did not derive it, but it is something, it is possible for you to derive it. I derived the scalar form of this week, but you can derive this one, is x transpose lambda x times w is x transpose lambda y, where lambda is a diagonal matrix. So, lambda will have lambda 1, lambda 2 up till lambda m if there are m sensors, and off diagonal is all zeros, and remember lambda itself is 1 over sigma square. So, if sigma is very low, it means it is a very highly accurate, low variance, like it always gives you very pinpoint results, then it means that such results should be weighted highly. It means you should, I in fact showed you an example this week of what happens when you weight a sensor highly. The line sort of biases itself towards it, okay. So, and the line will bias itself away from a sensor that is not so accurate. So, that is what we did. I hope this summary kind of gels together what we did this week and the overall theme. Next week we will move on to the case of non-linear regression, things that cannot be handled with simple linear models. So, that is it for this week. I hope you enjoyed this. I hope you do the exercise problems. There are a couple of exercise problems, main exercise problems this week. One deals with weighted least squares and one deals with the normal equations, sorry, the unsteady conduction case where you have to linearize and then do a linear regression. So, I hope you enjoyed this week's exercises. See you next week. Thank you.